Okay, so today I'll be talking about Boltzmann and Saha equations. Now, before I talk about this, let me little bit recap about what we did in a very short manner with absorption spectra. Well, what we have done till now is basically we have classified stars by their absorption spectra, right? Now, at the surface of the stars, basically the photosphere, we see absorption spectra. And when do we see them? Well, we see them when the gas near the surface absorbs light at wavelengths that are equal to the transition frequencies of the gas atoms. And the dark lines of the absorption spectra arise because the likelihood of a photon scattering of the gas at these frequencies is higher than at surrounding frequencies, and so the surface of last scattering is somewhat higher in the atmosphere of the star, where it is cooler and the luminosity is lower. Right. Well, we also know, we have discussed that originally the stars, they were classified alphabetically, remember? And when I say alphabetically, it means A, B, C, D, E, F, and this classification was done according to the strength of the Lyman series of hydrogen atom. So originally the classification was based on Lyman series of hydrogen atoms, right? Yeah, hydrogen lines, right. Now, but it was later shown that the relative strength of the Lyman lines is basically related to temperature, but again not in a regular manner, right? As a result, when arranging according to decreasing temperature, the alphabetical ordering is lost, and the sequence is now given by O, B, A, F, G, K and M. Now, you see, the relative strength of these lines is basically related lines. This is basically related to composition and the temperature of outer stellar atmosphere. Now, this relationship is described by using a combination of both Boltzmann and Saha equations. So, we will be talking about it. Now, the Boltzmann equation, basically this one is basically describes the relative number of atoms in different excited energy levels, whereas the Saha equation, it describes the relative number of atoms in different ionization states. Okay. Now, in local thermal equilibrium, the amount of energy in excited atoms should be in equipartition with the kinetic energy of the atoms, and as a result, the number of atoms that are in required excited state to absorb a photon is related to the temperature of the gas. Right. Now, you see, the atoms in the stellar atmosphere, what is their speed distribution? Well, we do know that they have a distribution of speed which is described by Maxwell-Boltzmann distribution, right? Let me write it down here. So this is the equation, speed distribution, equation 1. Let me write it. And well, what are the various terms here? You do know, right? What is this NV? This is basically the number density of atoms with speed v, right? What is this N? N is the total number density of atoms in gas, and this M is the mass of atom. Now individual atoms, they gain or lose energy through collisions, and so the distribution in kinetic energy of the atoms produce a characteristic distribution in excitation levels in the atoms. Now let you say, let SA, small sa be the specific set of quantum numbers associated with a state of energy EA. So A say EA, and similarly let S be, this is small s, okay, be the one associated with energy EB. Then you see the probability, the ratio of the probability that the system is in state B relative to state A. What will it be? Well, it is given by this relation here, right? This is equation 2. Okay. Now, if there are several states with different sets of quantum numbers but the same energy, then we know that these states are degenerate states. Now, if there are degenerate states, then what happens? Of course, there are, right? Now, so if there are degenerate states, then what do? We basically, so for degenerate states, what we do is we introduce statistical weights GA and GB, which are basically the number of states of each energy. And so this probability ratio, this basically becomes like this, okay, equation 3, where, well, Na is the number of atoms with energy EA, right? And same for NB, number of atoms with energy EB. Now let us go through an example. Now let us just consider calculating the temperature at which we can expect equal number of atoms in the ground state and in the first excited state. Okay, so we will consider an example, and the example is calculation of temperature at which we expect equal number of atoms in ground state, that is n is equal to 1, and in excited state, first excited state. First excited state. That means n is equal to 2. Well, this is n is equal to 1. Okay. Yes, and this is n is equal to 2. Now, why is this example important? Do you know? Well, you see, it is really important, this example, because the Lyman series of absorption lines arise from atoms that start in the first excited state. Now, there are two ground states corresponding to the two spin states allowed for the electron. So, G1 is equal to 2. Whereas, in the first excited state, there are 4 orbitals corresponding to the s and p orbitals and 2 electron spin states allowed for each orbital. So, there are a total of 8 excited states. So, this means G2 is equal to 8. Right? Now, the energy of the ground state, right? For hydrogen, of course, we are talking about. So, energy for the ground state is E1 minus 13.6 EV. We know that. So, let this be minus E0. And the energy for the first excited state, again we do know for Bohr theory, this is equal to E1 by 4. Right? Now, what we require is basically N1 is equal to N2. Right? And so, this means we want this thing. By 4 kVt. Right? Now this is equation 4. Even though we are talking about example, it is good to write it, nomenclate this equation. Now this, when solved, this thing can be solved to give temperature around having this value. You see? You can check this yourself, students, and you will find that the value comes out to be this. Right? So, basically, this is approximately 85,000 Kelvin. Therefore, at about this temperature, 85,000 Kelvin, there should be roughly equal number of atoms in equal number of atoms in first excited state and in ground state. Right? Now let us compare with the observations. However, when we compare with the observations, we find that the maximum intensity of hydrogen lines coming from absorption in the first excited state comes at about observations, right? So the observations, they show that the maximum intensity of hydrogen lines coming from absorption in the first excited state, and this comes from about 9,500 Kelvin. Now look at this. These numbers are largely different. Right? So this means we miss something. Okay? So we are missing something. This is important. Come on, you just see the calculation, and this is observation. Roughly 9 times the difference. Right? So this means that our theory is missing something, and we have to find it out. Well, you see, what we are missing is the fact that at higher temperatures that atoms can be ionized. Right? So what we miss is the fact that at higher temperatures, atoms can be ionized. Now, since an ionized hydrogen atom cannot absorb a photon, right? Ionized means the proton and electron are just separate. Okay, there is hardly any atom again. Okay, so they cannot absorb a photon, so only the total number of neutral hydrogen atoms compared to the strength of the absorption lines. This is important. So only total number of neutral H atoms contribute to strength of absorption lines. Now, as the temperature increases, the total number of absorbers decrease, even as the relative number of atoms in the excited state increase. Therefore, in order to accurately describe the strength of hydrogen lines in stellar spectra, we also need to calculate the number of atoms in an ionized state relative to the number of atoms in an unionized state. You understand? Okay, and Saha equation now enters the picture. So, you see, Saha equation basically, Saha equation of ionization, basically it provides a way of calculating the number of atoms in different ionization states. Now, a neutral atom is basically a neutral atom. Well, what about its ionization state? Well, we can say that it is in an ionization state atom. So, it is in an ionization state. I is equal to like this. We write 1I. Okay. Okay. Now, a singly ionized atom. What about it? Its ionization state is given like this, Roman number 2. Well, a doubly ionized atom, its ionization state, let us introduce this nomenclature and so on. And we also define this Ji as the ionization energy required to remove an electron from an atom in ground state, taking it from ionization state I to ionization state I plus 1. Okay, now then in this case, well, you see the partition function gives the weighted sum of the number of ways an atom can have a given energy. Okay, well, we do know this from statistical mechanics. And let me write down. Yes, so this is the partition function, and this is equation 5. Well, here E1 is basically the ground state energy for the given ionization. Now, the ratio of number of atoms, so the ratio of number of atoms. So this one is partition function, right? Now the ratio of number of atoms in two adjacent ionization states is given by, you see, this equation here, and this is our Saha equation 6. This is the famous Saha equation. Now you see, for an element X, this equation results from considering the thermodynamic equilibrium of the reaction. So this is our Saha equation. Now I am not going to derive this here. You students, you can refer to statistical mechanics class. I am going to talk about the applications. Well, but how do we get this? Well, for an element X, this equation, how does this arrive? Well, it results from considering the thermodynamic equilibrium of the reaction Xi plus 1. Yes, this is important. Now we can also express this in terms of the free electron pressure. So we can also express this equation in terms of this. Of course, where we have assumed ideal electron gas, and in that case the equation will become like this. Okay, so this is equation 7. Now what about the strength of Lyman lines in a star? Well, this is what we are actually probing. So our aim, remember, our aim is to calculate or understand the strength of Lyman lines in a star. So now we have talked about the Saha equation. So let us see how we calculate this, and if we can really get this number. This is important, which was experimentally observed, right? Now you see, the strength of the Lyman lines in a star, this is basically proportional to the ratio of the number of H1 atoms in the second excited state N2 to the total number, okay, total number of hydrogen atoms. And what is that? You can write it as N total. Right. Now it is important to note that N total, this includes both H1 and H2 atoms, right? And since we know from observation that the temperature of interest is around this 10 to the power 4 Kelvin, right, 10,000 Kelvin, so we can assume that all the H1 atoms are either in ground or first excited state. So what happens then? Well, therefore the total number of H1 atoms is, so total number of H1 atoms is N1, sorry, not N1, Ni, yes, Ni, approximately equal to N1 plus N2, and thus we can write, you see, this relation. We can write this. Yes, you can see. So I'm just doing a sort of introducing N1 and then writing it like this. Okay. Yeah. So what is the equation number? 6, 7. So this is equation number 8. Okay. Now for hydrogen we have, you see, N2 by N1, this is equal to 4 power minus beta delta E, right? Where this beta is equal to 1 by kBt, and also this is 1, and also delta E is basically E2 minus E1, right? And this is equal to 3 by 4 E0, which we introduced. So E0 is basically 13.6 eV. Now there are no electron energy levels for an ionized hydrogen atom, and so this means that Z2 is equal to 1, and then this means that the leading terms of the sum for Z1 are 2 plus 8 to the power minus beta delta E, and plus so on and so forth, right? Now, so finally we can write, you see, using these relationships we can write this ratio here. Yes, this Z1, this is equation 9, and here this is equation 10. Okay. So with this we will finally arrive at this result. Finally we will arrive at this result here. Now it may look very cumbersome, but it can be solved. I mean, we can plot this, right? And you will be very amazed to know that this equation, when plotted, you know how does it look like on plotting? Well, let me show you. Yes, here. So yes, so this basically is what we get from solving this equation, this important equation. And this equation, when plotted, it gives us this value. So what do you see here? Basically fraction of hydrogen atoms that are in the first excited state for the stellar atmosphere, and these calculations have been done assuming P is equal to 20 Newton per meter square. Now what is important to note is the rise at low temperature, and this is due to the increased number of excited atoms, while you see the drop at higher temperatures is basically due to the increased number of completely ionized atoms, right? So this rise is due to increased number of excited atoms here, and this one is due to increase. So this is due to, this rise is due to increased number of excited atoms, and this decrease on the higher temperature is due to the increased number of completely ionized atoms, right? And what does the peak come around? Well, this peak here, this one, you will be amazed to know that this peak comes at around 9900 Kelvin. Hooray! You see, so this is quite or very much close to the observed value of 9000 Kelvin. Observed value. So this means that using Indeed, using both Saha and Boltzmann equation, we are able to confirm the strength of Lyman series in a star and confirm that this is indeed happens, the peak happens at around 9000 Kelvin. Okay, so this is an important application of Saha equation for stellar case.